Hi, let's look at one more example of Newton's third law and really Newton's second law when it comes to thinking through situations. So, during a softball game, a line drive is hit toward Shirley, the shortstop, who reaches her glove out to catch the 0.185 kilogram ball. The softball was moving at a speed of 16.4 meters per second when it first hit her glove, and Shirley's glove naturally recoils a distance of 7.55 centimeters as she brings the ball to rest. So, number one, calculate the acceleration of the softball. So, if you recall, we can typically find the acceleration of an object if we know the net force of that object, the net force acting on that object and the mass of the object. We know the mass of the softball. We're not given any newtons of how much force is acting on the ball, and there's no real way to know how much force is acting on the ball. And so we need to go about finding the acceleration in a different way, one that uses the pieces of information that we are given. So when I look back at the problem, I see some information here about the ball's speed before it started to slow down when it hit the glove. I see the ball came to rest at the end of its motion. And I also see that the ball and the glove travel a distance of 7.55 centimeters as it's being brought to rest. So I see this information. I need to translate this information into really what it represents about the ball's motion. So this is where the tricky part comes in. You need to think through what do these values actually represent about the ball's motion. So it says it was moving at a speed of 16.4 meters per second when it first hit the glove, and then it comes to rest. So this tells us the initial and final speeds. Initially, the ball was moving at 16.4 meters per second, and then finally, it ends at 0. And so we know the initial speed of the ball is 16.4 meters per second, and the final speed of the ball is 0. We also are given that the glove with the ball in it naturally recoils a distance of 7.55 centimeters while the ball is coming to rest. And so this tells us that the ball moves a certain displacement while it is slowing down. And so we're going to say that that is delta x. So real quick, I noticed that the displacement is in centimeters, but typically when we're dealing with speeds and distances, we need this to be in standard notation, standard units. Also, I noticed that the speed was given to us in meters per second and not centimeters per second. So we need these units to agree with each other if we're going to be able to do any kind of math with them. And so we need to convert this 7.55 centimeters into meters. To do that, I'm going to multiply by the conversion factor here. And so I want to get rid of the centimeters. And so I'm going to multiply by what the centi represents. And the centi represents 10 to the negative 2. So I'm going to end up basically dividing by 100. That's what all this means here. And so the displacement of the ball is 0.0755 meters. So we're looking for the acceleration, and we know the final velocity, we know the initial velocity, and we know the displacement. So we need to look for an equation that has these pieces in it. The one thing that I notice we're missing here, if I'm really thinking about it, is we don't have the time that the ball took to slow down. So we're not going to be able to use any equations that need a time value. So if you look through all the previous equations that we've used up to this point, there's really only one equation that has acceleration in it, but not time. And that equation is this one. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times delta x. This equation has all the pieces that we need, and we're really trying to solve for the acceleration. So we have the final velocity, we have the initial velocity, we're looking for acceleration, and we have the displacement. So this equation will do the job for us, assuming we can do the math parts correctly here. So let's substitute in our numbers. The final velocity is 0. The initial velocity is 16.4 meters per second, and that gets squared, plus 2 times the acceleration times the displacement, which we converted into meters. Okay, so I'm going to simplify this as much as I can. I'm going to do some math here. 16.4 squared is 268.96. We don't need all those decimal places. We can just deal with 269. That'll be our value here. And that's meters squared per second squared, because the square goes to the number and to each of the units. And then that's going to be plus. And then I'm going to go ahead and multiply together what I can. So the 2 can be multiplied by the 0.0755. So I get 0.151. And that's meters, and that's still times the acceleration. So I just went ahead and multiplied this 2 and this 0.0755 together to get 0.151 meters. All right, now we're going to do some more algebra here. We're solving for acceleration. We need to get rid of whatever's next to it, starting with the farthest from it. So we're going to subtract 269 from both sides of the equation. All right, so that's going to get rid of it on this side. We're going to be left with negative 269 meters squared per second squared, and that's going to be equal to 0.151 meters times the acceleration. Now we can undo this multiplication by dividing 0.151 meters. We're going to do the same thing to both sides here to keep it equal. All right, so that cancels this out completely. The meters cancels out one of the meters up here. And so we'll do the math in our calculator now. It's going to be a high number here. So 269 divided by 0.151, that's going to be 1,780. We're going to round that, so we only need 3 digits there. So that's going to be negative 1,780 meters per second squared. This is the acceleration of the softball. It's negative because it's slowing down, and our original speed was in the positive direction. So this acceleration is against the original motion of the ball. So that's why it's negative here. Now that we found the acceleration, that's probably the hardest thing we'll need to do, because from here, the equations are much simpler. It says number 2, what is the average force in newtons applied on the ball by the glove? So the ball is slowing down, and it's slowing down because the glove is applying a force to the ball. It says average force here, and in this case, we're talking about average force because, technically speaking, the ball does not experience a constant force from the glove. It might vary a little bit throughout the slowing down process, but we're going to call it the average force, and basically that's just to be technically correct, saying that the force may change a little bit, but overall, what's the average force? We can essentially ignore this word because we're just looking for the force being applied to the ball. Now we can use Newton's second law to find this force. The net force on the ball is equal to the ball's mass times its acceleration. The net force is the applied force in this case. There's no other forces acting on the ball except for the glove. And so the force on the ball is its mass, which is 0.185 kilograms times the acceleration that we just found. All right, so we'll put this into our calculator. 0.185 times 1780. So 329 will be our answer here. Negative 329 newtons on the ball. Again, the ball is moving to the right in our example, and so the force on the ball is negative, just to say that it's acting against the ball's motion to slow it down. So when you try to answer questions like this, you may not need the negative sign in there. So what is question 3? What is the average force in newtons applied on the glove by the ball? So this is where we use Newton's third law, and we know that for every force, there's an equal and opposite force. So if the glove is applying a force of negative 329 newtons on the ball, then that means the ball must be applying a force of positive 329 newtons on the glove. And that's because for every force, there's an equal and opposite force acting. So that should solve this problem. And that's all I've got for you in this video. So remember, confusion is the sweat of learning.